we're going to look at tonight is some further analysis of real transformers. So we're going to look at how that model, we developed this complete model of a real transformer. But in actual fact, when that's loaded, that can be very much simplified under loaded conditions. But you need to, when you do a simplification, you need to know what the implications of that are. So it's important to know what components are in the full model to understand the limitations of the simplified model. So we're going to look at how we can determine model values for a practical transformer using closed and open circuit tests. So we're going to look at some ways that that can be done, and then from that we're either going to work through the transformer on the rig, albeit that we can't actually do the practical. Or I'm speaking now with Mr. Collicott here as to whether he can find a transformer at work and do some tests on that for us, bring some data in so that we can model that. On that note, I didn't really think about your situation, Roger, but what access would you have to a mains voltage transformer and the ability to do some tests on that?
That should be okay.
Yeah, well, what we'll do is if we go through tonight's session, you'll get a good idea of what would need to be done. And then if between us we can get some transformer tested and some data. I think the hardest thing, as Robbie and I have been discussing before you all come along, is finding a suitable load for it of a known resistance. That's going to load up to kind of at least 50% of its full load. But we'll have a little bit of a chat if we get time later. And if not, I can always use the data I've used every other year. It's just that we won't actually be able to see it on the rig. All right?
Okay.
So this is we're going to look at simplifying the transformer model, as I said. Now, what we've got in the diagram here is the full transformer model. So it's got its R1 and X1 as the two series components representing the resistance of the windings and the leakage flux in the primary winding. That's got R2 and X2 in series in the secondary, representing the resistance of secondary windings and the secondary leakage flux. And then that's also got your two IO components, which is your RC, which is the resistance of the core, the heating effect of the core, and XM, which is your magnetizing current, magnetizing flux. Okay, so and this is showing that transformer model without any load on it. So the secondary terminals at open circuit. So this circuit gives far more detail than is needed to solve most practical problems regarding transformers. It's possible to simplify this model by considering its action separately when it has no load and when it has at full load. Okay, so we're going to look at the two separate situations and see how we can simplify this model into something that will help us to do a reasonably good analysis of a real transformer. Yep.
Yep.
So if we look at this real transformer diagram with no load, if there's no load, there's no current I2 over here. Let's just make it red. Put the size down a bit. So no current flows here, I2. Yeah. Because, and if there's no current flowing in the secondary, because this transformer is ideal, then there's no current flowing in this bit here either, beyond that node. So if there's no current flowing out of the ideal transformer, then there must be no current flowing into it. Okay?
Yep.
What this means is that the components R2 and X2 over here have no effect and can be ignored. So down the bottom in our simplified model of a transformer offload, we just take out the two components R2 and X2. They don't do anything. Okay, then the impedance of R1 and X1 at no load condition are so small because the volt drop across them is so small that they'll be negligible compared, because the IO current is much less than would flow in a loaded condition. The volt drops across these two components is negligible enough to be ignored. Yeah, so we can take them out of the circuit as well, and we've done so in the diagram at the bottom. So we've got a revised equivalent circuit for a real transformer at no load, and that's as shown below. Yeah, so as to what we looked at initially for the open circuit transformer, where we didn't consider the R1 and X1 anyway, we just considered these three components here. All right.
Mm-hmm. Yep.
Okay, and the transformer ratio, if we had a transformer like that, we can get the ratio by measuring the voltages that we put in at EP and ES would give us our N1 over our N2, or the transformer ratio A. All right?
Yeah.
Everybody happy with that?
Yeah, fine.
Okay. Now, the real transformer with full load. All right? So that's what we've got up the top there. Imagine that ZL connected to the output is a suitable impedance to fully load this transformer. At full load, primary current IP over here, this one, is at least 20 times the size of the current IO. Yeah, this means that the components RM, that should be RM really, that should, and XM can be ignored. Their effect is so small at full load that we can take them out, which is what we've done in the bottom diagram. Okay, so on full load, we forget about the two components that represented the situation on open circuit. So our revised transformer model is we've got R1 and X1 in the primary and R2 and X2 in the secondary. And it's suitable to use this model with transformers loaded down to as low as 10% of their maximum rated load. Yeah. So unless you're going really low in loading, and why would you do that? Why would you put a transformer in that's rated at more than 10 times what you actually want to use it for, unless you're building in redundancy, I suppose. Yeah. Okay. Everyone happy with that?
Mm-hmm.
Good. Right. Further simplification. Now we've done this transfer and impedances across we were working on last week and the week before. It's possible to further simplify the model under load by transferring the secondary impedances to the primary side and removing the ideal transformer. So we've still got our R1 and X1 here, yeah, and then we've transferred our three impedances. So we've multiplied R2 by A squared, we've multiplied X2 by A squared, we've multiplied the load by A squared, transferred them all to secondary, and our current here, our voltage here is A times E secondary, and if we put I in there, so that would be I2 over A. Yep.
Okay. Yep.
So I2 over A is equal to IP, the primary current here. They are the same in this particular instance. All right. So again, we've now simplified the model a little bit more, and we can ignore the ideal transformer because we've transferred the impedances across. Yep.
Yep.
Everybody okay with that?
Yep.
Lewis?
Yeah, all good. Thank you.
Yeah, that's right. Good. So then what we can do is, from the model on the previous page, we can combine the two values of R and combine the two values for X into one R and X in series. So the primary and secondary, primary reflected and secondary, the primary and reflected secondary impedances can then, if need be, combined into one single resistance reactance. So if we're not interested in separately knowing what these components R1, X1, A squared R2 and A squared X2, what they do separately, and the separate volt drops across them, for instance. If we're not interested in that, if we're only interested in the overall action of the transformer with its terminal voltages and currents, etc., then we can combine them together into one R plus X impedance in series. Yep. So this R here is R1 is R2A squared, and this X is X1 plus X2 A squared. Yeah.
Yep.
Because most times, all we're going to be interested in is how much do we lose because of these two overall components from here to, from the primary to the secondary. What effect does the overall, remembering that these two components represent the overall loss. I don't know what's up with mine. I reckon my pencil's batteries run out. Okay. I'll give you something to do in a minute, and then I'll see if I can charge it up. So those two components there represent the overall loss, and in most cases, the overall loss and what the phase angle is, perhaps between the thing adds to the situation, is what we're really interested in. Okay.
Mm-hmm.
Everyone happy with that?
Yeah, fine.
Yeah. Right. What we got on the next page? Okay, we've got a problem. First example of the evening. So I'll get you to have a go at this, and then we'll work through it together afterwards. So, analysis of open circuit transformer. For the transformer shown, nominal rating is 200 kVA. the nominal E primary as shown, 11 kV. So these things here, nominal, are what you'd find on the rating plate. Nominal secondary, 400, yeah, volts. RC is given as 27.5 K, and XM is given as 16.5 K. Use the simplified model, so that means that you can do away with R1, X1, R2 and X2, and use the simplified model of the open circuit transformer to find the open circuit primary current, the power loss in the core, and the reactive power used to magnetize the core. So it's asking you to find the current IP, which will be IO in this case, and excuse me, the power loss, so that's the power dissipated by the resistor, and the reactive power, which is the Q used to magnetize the core. All right, so have a go at that problem, and then when you had a go, we'll go through it and see if you got the right answers. All right. Okay, so talking through this for the video, we've tackled this problem by finding the total impedance first, using product over sum. So that's RC times XM divided by RC plus XM. So taking the numerator, it's 27,500 resistance to the resistor, and it's got an angle of 0. And then the 16,500 of XM ohms, and that's got a, because it's an inductor, angle of 90 degrees. Multiplying those two out, complex polar numbers, you get 454 times 10 to the 6 at an angle of 90 over here. Then the denominator, we want that in rectangular form, so we can add the two together. So there's the 27,500 real part from the resistance, and 16,500 plus 16,500 J representing the inductance. Using the calculator, then to convert that to polar, we get 32,020 angle 31 degrees. Then doing that polar division, we end up with a total impedance 14.2 K ohms, angle 59 degrees. You can then use that total impedance in Ohm's law with the voltage to find the total current, which is 0.78 amps, angle minus 59 degrees. Checking that with our favourite word, civil, we've got an inductive circuit, and current should be lagging voltage, and it is, it's got a negative angle. You could have also tackled this question in a slightly different way by using Ohm's law, EP over RC, to find the resistive current, IC, and then EP over XM to find the inductive current, IM, and then taking those two complex currents, add them together to find IO, and you should get the same answer. So moving on to part B, it's asking for the power in the core. So this is the power dissipated in the resistor. We have three options to find power. That would be the current through the resistor squared times R. We don't know the current through the resistor unless we pick the second option on part A of the question. We could also use the resistor current times the voltage, EP, but we don't know the resistor current at this stage. But one option we do have, because we know the value of the voltage applied and we know the value of the resistor, we can use the third option for finding power, as E squared over RC. So if we use that, 11,000 squared over 27,500 ohms gives us a power in the core, power loss in the core of 4,400 watts. Okay, and then part C, I've left you guys to find the reactive power Q. Presumably what you've done, Robbie, is said Q is equal to the applied voltage squared over XM, yeah?
Yep.
And that's 11,000 squared divided by 16,500, which is 7,333 var.
Yep.
Yep. Okay. All right.
Yep.
Everybody happy with that?
Yeah, that's fine.
Yeah, all good.
So that's analysing using the simplified model of a transformer, the offload situation. Yep.
Yep.
Right. Now the onload situation. So the diagram there of the full model. Okay, we're going to use the simplified full model. So take away the components and ignore RC and XM. Being given a nominal rating as 220 kVA. So this is it's a big 11 kV down to 400 transformer. EP 11 kV, ES 400 volts. Turn ratio is 27.5. R1 2.7 ohms, X1 13.7 ohms, R2 4 milliohms, X2 20 milliohms. So you got all the values you need there. The transformer's loaded with a load of 2 plus 1.5 j ohms. So I've given you a complex load here. It's an impedance rather than just a resistor. And the generator supplying the nominal voltage. So you can assume that the applied voltage is 11 kV. So you would expect under nominal conditions to get 400 volts out the other side. Okay. So what this question is asking you to do is calculate the primary current, the voltage at the secondary terminals ES, and the current flowing in the load Z. And if you look on the next page of your handouts, you've got the diagram that we looked at before where we discussed, just make mine a little bigger. We discussed moving the secondary impedances across to the primary side to do the analysis. So how let's just, rather than you go off and struggle, let's discuss a plan of action as to how you'd go about solving that problem, finding the primary current. What do you think you need to do first?
So you're going to need the total impedance again, aren't you?
Sorry?
Are you going to need the total
impedance? Yeah. So plan of action is total impedance. Yeah.
Oh, then if you then use Ohm's law, that'll give you the current.
Yeah, that'll give you that current. You can then find the current. So that would be that would give you the primary current, yeah? Then you're being asked to find this voltage. But what you're going to find is A times ES. So then you've got to find just ES.
Okay, so
Yeah.
Yeah.
So you're going to find IES, transfer back. Yeah.
Mm-hmm.
And then the current flowing in the load, well, you've found IP in the first part. So you've got to convert that to that IP is also I2 over A. Yeah. So find I2 over A. Well, you've got I2 over A. Convert that back. Yeah.
Yep.
So have a go at that and see how you get on.
Okie dokie.
Here we go. So I've calculated up the top here, R2 dash, or by multiplying A squared by R2, 3.025 ohms, and X2 dash, 15.1 ohms. Then I've multiplied each of the separate parts of this complex impedance by 27.5 squared to end up with the load ZL dash 1513 plus 1134J ohms, and convert that to polar in case I need it later, 1891 angle 36.9 degrees. Yeah, you all get that far?
Yep. Slightly different angle, but that's probably just around there.
Yeah, but yeah, it could be. And if you've done that double conversion as well, so
yeah,
ZT then can be R1 plus XL1J plus R2 dash plus X2 dash J plus the ZL dash, which is, I'll just leave it as that for the minute. So that is R1 is 2.7 ohms plus X1 is 13.7 J plus 3.025 plus 15.1 J, and then ZL is 1891 plus 1134 J. Yep. And we add up all the resistive parts separately and all the reactive parts separately. You should have 1519 plus 1163. I got an echo. All right, that's in rectangular form, but to calculate the current, you need to convert that to polar. So that converts to 1913 ohms, angle 37.4 degrees. You managed to get that far?
Yep.
Robbie? Roger?
Yeah.
Yeah.
Yep. Good. Okay. I'll just take that with me. To a new page. Yeah. So we can go.
Sorry, Mike.
Yeah.
I need to go back 1 second. Just onto the last
Yeah, I
page.
can. Of course I can. Yeah. There you go.
I'll take a photo of it. That's fine, and then quickly write it down so you can carry on.
You all right? Yeah.
Yeah, it's
Good.
fine. Yep.
Yep. Okay. So then we can go. Therefore, IP, the primary current, is equal to EP of the total impedance, which is 11,000 angle 0 over 1913 angle 37.4 degrees equals 5.75 amps angle minus 37.4 degrees.
Mm-hmm.
And that's a lagging current, which we would expect in an overall inductive circuit. Yeah.
Yep.
So is that what you got?
Yeah, that's what I've got. I'm not too sure about how I've done after that, but I'm pretty fine with that so far. Yeah.
Okay. Yeah. Roger?
Yeah, okay. Yeah.
Yeah. Right. So the next part of the question, I believe, is asking for what is the secondary terminal voltage, yeah?
Mm-hmm.
So I'm going to go on a new page rather than do half of it on this page and half on the other, because I want to draw a diagram. So I'll do it over here. What we got at the moment is we've got our EG that we know is 11 kV, and we've got an impedance here.
Is that EP?
Sorry?
Is that EP?
Yeah. The primary voltage would be
Yeah.
what was coming from the generator, yeah, 11 kV.
Yeah.
All right. And we got ZL dash in here. That is 1891 angle 36.9 degrees. Yeah. And we've calculated the current I as 5.75 amps angle minus 37.4 degrees. Yeah. Going to neaten that up a bit. Can't really see that. One 891 angle 36.9 degrees. Yeah. What we're looking to find is this voltage here, which is E2 dash, and then we can transfer it back to the secondary side and find out what it is on its own side. Yeah.
Okay.
So we can use, we know the current, And we know the impedance of the load, therefore we can go E2 dash is equal to I primary times ZL dash. Yep.
Okay.
Happy with that? Okay. Therefore, that is 5.75 angle minus 37.4 degrees multiplied by 1891 angle 36.9 degrees. You don't have to put these in brackets, but I find that helps to make sure you get these right. Yeah. So E2 dash is equal to, I got 10873 volts angle minus 0.5 degrees. Got that right, and I asked minus 37.4 plus 36.9. Yeah, minus 0.5 degrees. Okay?
Okay.
Yeah.
Yep.
Then,
Oh, hang on. No, I've got minus 74 degrees. Hang on.
you're multiplying, Robbie, so it's minus 37.6.
Oh, I need to add them, yeah.
Yeah, plus 36.9.
Yeah, okay.
Yeah.
That's where I've gone wrong now.
Okay.
Yep.
So therefore, we can now convert back. So we can do E2. So we're converting this back to its own side.
Mm-hmm.
Is E2 dash divided by A.
Yep.
That's 10873 angle minus 0.5 degrees divided by 27.5. E2, that's the terminal voltage on the secondary side, is equal to 395 volts angle minus 0.5 degrees. And that should be because they're primary and secondary in phase with each other.
Yeah.
Yep. So where the nameplate says for 11 kV in you should get 400 out, because of the losses we're actually only getting 395. Yep.
Yep.
And then the last part says find the secondary current. So another new page, we can go, we know what I2 dash is, that's the 5.75. So we can say I2 is equal to I2 dash times A, which is 27.5 times 5.75 angle minus 37.4 degrees. When I multiply that out, there's 158 amps angle minus 37.5 degrees. Alternative method is that we use that secondary voltage we just calculated. So we can go I2 is equal to E2 over ZL. So that's the 395 volts angle minus 0.5 degrees. we need to convert the over 2 plus 1.5J. So we need to convert that to polar form, 395 volts, angle minus 0.5 divided by, and the conversion on this is 2.5 angle 36.9 degrees. Yep. And if you do that, you get 158 amps angle minus 37.4, which is slightly different. That's just because of a different method. The error in converting the 2 plus 1.5J over to polar, I would think. Okay?
Yep.
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 Right. Everybody else happy?
Yeah, fine.
Yeah.
Yeah, all
So
good.
have you all got the second set of notes that I sent you a little while ago?
Yep.
Yeah.
Does anyone want to print them out or anything?
Yeah, I've already printed mine. I'm all good.
I'll just stop the recording for a minute anyway. I just need to open another file up now on the iPad. Right. So what we're going to look at now is determining the transformer's impedance practically. So we can do this by carrying out two tests, an open circuit test and a short circuit test. So first of all, we open circuit the secondary and apply the normal primary voltage, AC. We measure the power input for the primary, the secondary, the primary and secondary terminal voltages, and the primary current. And we record those readings. And then we short circuit the secondary. We measure the power input, the primary terminal voltage, and the primary current. Care is needed when performing short circuit test so that you don't go over the VA rating of the transformer. So you'd put a much lower primary voltage on for the short circuit test, as will become clear. So when you do that, so here's our circuit, open circuited the secondary and just connected a voltmeter to measure the secondary voltage. We've got a voltmeter on the primary side to measure EP. We've got an ammeter to measure the current. We've got a wattmeter to give us the power. So the wattmeter will give us PM, the power dissipated in the core. The apparent power we can find from EP times IP. We can then use Pythagoras theorem because we've got S and P, and therefore we can find Q. The resistance of the core loss is given by RC is the voltage primary squared divided by the power. So we've rearranged P is equal to E squared over R to find RC. And then could do the same for the magnetizing reactance, do an EP squared over Q to find XM. And the last piece of information this will give us is a turns ratio of the transformer by dividing EP by ES to give us I. So that's the information that we get from the open circuit test. Then the short circuit test, we short the secondary side with a piece of wire. When I do the one at the college, I'll put an ammeter in to make sure we don't overdo the current on the secondary side. Put a much lower voltage for a mains transformer, maybe 12, 24 volts AC on the primary side. We measure the watts, the current, and the voltage. Yeah, and from that we can get the transformer impedance referred to the primary, that's ZP, is equal to the voltage of the current. And then transformer resistance. So these are this value here. Refer to the primary is the power divided by the current squared. And then we can use Pythagoras theorem over here, because we know Z, we know R, we can find XL. We've now got the components for this transformer. We know EP, we know R, we know X, and then the open circuit tests, we found the value of the parallel components. So, working on this example, we're looking to find these two component values so we can load the transformer with 50 ohms. And then we've also got the values of RC and XM for the offload conditions. So we'll go through the solution shortly. So we're doing primary current 0.15 amps times the primary voltage 69 kilovolts gives us 10350 VA. Yeah, well below the rating of 69 kilovolt. I think it was 100 some odd kVA, wasn't it? From the original question, I think. 500 kVA. Yeah. So then we can find QM by the fact that we've now got two sides of the power triangle. We've got P and we've got S, so therefore we can find Q. That is the square root of SM squared minus PM squared. So that's square root of 10350 squared minus 5000 squared. And I've got 9062 var. Yeah.
Yep.
Yep, just checking it.
And then, now we know that, we can find the value of RC, the resistor, in parallel from EP squared over PM. That's a rearranged power as equal to voltage squared of a resistance. Rearrangement of that formula has 69,000 squared divided by 5,000. Equals 952200 ohms, which is 952 kiloohms. Yeah. And also, sorry, who's that?
I get Q, so that's what I was. Yeah.
You struggled with how you're going to get Q, Robbie?
Yeah, no, I've got it now, but the first
Yeah.
part I see, but there I sort of, I went a bit
Yeah,
back.
never forget them triangles. Yeah, if you've got two sides, you can always find the third side. Yeah, so that's really important that you remember about them. All right, and we can get XM from, as we said earlier, EP squared over QM. That is 69,000 squared over the 9062. Which is 525380 ohms, 525 kilo ohms. Yeah. The other thing we can find from this test is that A is equal to 69,000 divided by 4160 equals 16.6. Yep. Everyone follow that?
Mm-hmm.
Yeah. Okay. Then the other test.
Okay, I didn't do too bad on that then.
Yeah. So that's done the you found the values of RC.
Mm-hmm.
Hang on, we've got to find RC now. We've got RC and XM. Yeah, we've done that, haven't we?
Yeah.
RC and XM, yeah.
Mm-hmm.
So then we've got the short circuit test. These are the results. And from the short circuit test, we can find ZP from E short circuit over I short circuit. Admittedly, only the magnitude, but nevertheless, that's 2,600 the volts divided by 4 amps the current equals 650 ohms.
So that's labelled up as EP on the drawing. Is that supposed to be ESC? Is it? Or
on the diagram on my iPad, yeah. What it is E primary. That's E primary when the secondary is short circuited.
yeah.
I agree that's probably a little bit confusing
Yeah.
in a way, but that was kind of how I took it from a book. Yeah.
Yeah.
So that is the primary voltage. Is the primary voltage when the secondary is short circuited. Yeah.
Okay.
And that would be a voltage that you choose anyway.
Yeah.
Yeah.
Uh-huh.
And then you're measuring the current flowing in the primary when the secondary is short circuited, and you're measuring the power dissipated in the transformer when the secondary is short circuited at that given voltage and current. Yeah.
Yep.
Because what we're trying to do here is, if this is our simplified model, we're trying to find RP and XP, the total loss components, remember. Yeah, that's what we're trying to find, so that we can then connect our load across these terminals and do an analysis. Yeah.
Mm-hmm.
So we can get RP from power short circuit divided by I short circuit squared. So we'll rearrange the power as equal to I squared R formula. That is power's 2,400 watts. And the current is 4 amps, and we've got to square it. And the result of that is 150 ohms. Again, now what we've got is two sides of this power triangle, the impedance triangle, sorry. So we've got R and we've got Z, and so we can find X. So we can go XP is equal to root ZP minus RP. Both squared, they're squared. Yeah. That is root 650 squared minus 150 squared. 632 ohms. So we now know the two separate parts to this impedance here. So we know that the resistance is 150 ohms and the reactance is 632 ohms. Yeah.
Mhm.
So what we can do now is new page. Here's our model, e.g. I'm going to apply a EP of 69 kV. We've got an R component of 150 ohms and an X component of 632. They represent all the losses, the primary and the secondary series losses. Yeah. And then here's our terminals where our secondary would be. So this voltage here is E2 dash. Yeah.
Mm-hmm.
And then we're going to put our impedance over here. And we've got to connect Z dash. Yep.
Yep.
So to start this, we had to go ZL is 50 ohms. Therefore, ZL dash A squared ZL equals A was 16.6 squared times 50 equals 13778 ohms. So that's what we're connected here, 13778 ohms. Yeah.
Mm-hmm.
Now we can calculate ZT because it is ZL dash plus R P plus XP J. Yeah.
Mm-hmm.
We've got 13778 plus 150, two real parts to it, plus 632 J. Add the two real parts together to get a total impedance of 13928 plus 632 632J, which converts to polar 13942 ohms, angle 2.6 degrees. All follow that so far.
Mhm.
Yeah. So we can now find I primary, because it is EP over ZT. That is 69,000. Divided by 13942 angle 2.6 equals 4.95 amps, angle minus 2.6 degrees. Okay, everyone happy with that?
Yep.
Yep.
Yeah. So that's the primary current. I think that's one of the things that was asked for. I just need to check here what was asked for in the first place. RC, XM, voltage at the secondary, the active power to the load, power supplied by the source, and the efficiency. I'll just carry on with what I got in here. So moving on, the power supplied by the source. So the source is the generator, SG, must be the primary current times the primary voltage. That is 4.95 angle minus 2.5 degrees times 69,000 angle 0. That is 341,550 VA, angle minus 2.6 degrees. So that's the apparent power supplied by the generator. Now, one little tip is if you want the active power, the watts from that, is to convert it to rectangular. So we convert that to rectangular, we get 341,198. That's the watts minus 15494 J, and that's your VAR. So you've got your power here and your reactive power here. Yep.
Yep.
Just by converting that polar S into its horizontal and vertical components, because remember the rectangular form is P as QJ. Yep. Yeah. And this is S in here. And that angle in there, in this case, is 2.6 degrees. All right. So that's the power being delivered to the system by the generator in watts. It's 341198 watts. All right.
Yeah.
So how are we going to find the power dissipated in the load resistor?
So
Let's pop back to the diagram. Yeah, we want to find power, the real power in this load Z, which is per resistance, remember. Actually, boys, we're out of time here, aren't we? I'll tell you what we'll do. I'll leave you with that one, and we'll start with that one next week. All right? I lost track of time there. So if you have a go at that between now and next week, and then we'll start by going through the remainder of the solution. So my recommendation is you find out what E2 dash is, yeah, and then convert that voltage and this primary current back to its secondary value, and then use them to find S in the secondary in the same way as we've done in the primary. So find S, and then so we're looking at this, we found S in the primary, so find S in the secondary and convert it to rectangular to get the power out of it. So if you convert the primary current to the secondary side and find the volt drop across the load, E2 dash, and convert that to the secondary side, then you can do the same as we've done here on the secondary. You can do I secondary times E secondary to give you S secondary, and then get the power out of it from converting to rectangular form. But we'll start next week's session by going through the solution to that problem. All right?